Okay, good morning all the students. Let's continue with our sixth lecture under module 2. Yesterday we were not able to complete the concepts under the sixth lecture. So let us proceed with the same concept today also. So in that previous session to yesterday, we have seen what is the difference between restriction bias and preference bias. And we also understood that ID3 algorithm follows preference bias by selecting one of the optimal decision trees available in the hypothesis space. And finders and candidate elimination algorithms, they mostly follow restriction bias. Though they have lots of hypotheses available in the hypothesis space, still they try to restrict the number of hypotheses which are consistent with the training examples by reducing the version space size. Okay, and we also understood that Occam's razor indicates in any field when multiple optimal hypotheses are available, always go for the shortest and simplest hypothesis. That is actually being followed by this decision tree learning. Okay, so let us understand about issues in decision tree learning in more detail. In that issues, we have started discussing about avoiding overfitting the data. That is very important concept because that will mislead the machine learning experts and it may make them think that the models are performing very well by saying the training set performance. But actually the test set performance have to be noted down. Though the training set performance is very high, in some cases the test set performance will not be that high as much as this training set accuracy, which indicates overfitting of the data. Means the model has learned too much from the training examples and it is okay with any kind of combinations of the attributes, which will lead it to its less generalizability. Less generalizability means when some new data is given, when some unseen data is given, it will not be able to perform well with that. It will not predict properly with that data. In some cases it may predict well, but in some cases it may not. Most of the cases it may not predict well. Why? Because if a model learns too much from the training examples, then it will lose its generalizability. Means it can't perform well with the unseen data. That is why this trap of overfitting has to be cautiously avoided, right? So while understanding this avoiding overfitting of the data, we have seen how noise in the data or sometimes less training examples also lead to this overfitting. When there is noise in the data, say the decision tree tries to fit every possible outlier also in the decision tree by making the tree complex, by growing it to lots of levels, right? In such cases, that decision tree will not, though it covers all the training examples, though it makes all the training, though it is consistent with all the training examples, still it may not be able to generalize well with unseen data. It may not be able to predict properly the unseen data that is given to it. That is why decision ID3 algorithm tries to follow this Occam's razor theory. That is, always opt for short and crisp decision trees than going for long and complex decision trees. Okay. Now, in either of these cases, this simple algorithm, whether there is noise in the data or whether the number of training examples are too small, in that case, this simple algorithm can produce trees that overfit the training data. So you have to be cautious at that stage and see where to exactly stop growing the tree, where exactly to stop expanding the tree, right? That optimal point has to be noted. And we have also gone through the definition of this. Let me start the slideshow. We have seen the formal definition of this overfitting, right? Given a hypothesis space H, in this hypothesis space H, there will be lots of hypotheses, right? Now, a hypothesis H belongs to H is said to overfit the training data if there exists some alternative hypothesis H dash belongs to H such that H has smaller error over the training examples, but H dash has smaller error than H over the test examples or the entire distribution of instances. Entire distribution of instances, why we are using that term? Because the test and training set both will be taken from the same data set. And once the examples are taken from the same data set, they are said to have same distribution, right? They all behave in the same manner. Now, a hypothesis performing very well with part of it and not performing well with another part of it means that is not a perfect hypothesis, right? Say in a class, if all are fast learners, half of them are performing well with the same teacher, but others are not performing well. Means that is not a correct situation, right? In the same way, from a data set where the data is drawn from same distribution. Same distribution means all the data points in the data set behave in the same manner. In that case, if hypothesis is performing very well on part of data, that is on training set, and not performing properly on the test set, means it is not a correct hypothesis, right? That is what we mean by entire distribution of instances, entire data points in the in the data set, right? And now let's see this. Given a hypothesis space H, a hypothesis H belongs to H is said to overfit the training data if there exists some alternative hypothesis H dash belongs to H such that H has smaller error than H dash over the training examples, right? But what is the condition here? H dash has a smaller error, means H dash is performing better than H over the test examples. In that case, H is said to overfit. Why? Because it is not performing, it is performing well with the training examples, not performing well with the test examples. Means it is not able to generalize well on the unseen data. Test set is unseen by the model, right? It is not able to perform well on the unseen data. Then we obviously say it is overfitting. And H dash is actually performing better than H. Got it? That is the definition of overfitting. Now that we understood from this graph, we can see after specified number of nodes, say 25 nodes here, though the training data set accuracy is increasing, you can see on the y-axis accuracy being plotted and on the x-axis size of the tree. Now you're growing, the ID3 algorithm is growing the decision tree. Now, when it constructed the decision tree up to 20 to 25 nodes, till then training and test set performance increased. But after that, though the training set performance increased, the test set performance started falling down. It started reducing, it started decreasing. Did you notice this? Why? Because your model is learning too much from the training examples, and it is okay with every possible alternative where it can't generalize well for the test example. That is why the test performance is reducing, though the training performance is increasing. This phenomena is called as overfitting of the data, right? You need to understand this. This graph is very clear to you now. This solid line is training data accuracy or training data performance, and dotted line is test data accuracy or test data performance. Now, how we understood about this performance is by adding a new training example, which is actually correct. Means the end label should be actually S, but because of some wrong recording of the data, it is taken as no. Now, this is added to your 14 training example data set, where the model is trained to predict whether tennis will be played on a particular day when the weather condition is given, with respect to attributes like sky, humidity, wind, outlook of the sky, etc. Right? Now, if this example is added, in order to fit this training example, the decision tree will be expanded further. Now you see the first decision tree in this chapter, it has only 2 levels. Now in order to fit this training example, it may expand to 3 or 4 levels also. Because of the cause of an outlier, because of the training example which is wrongly recorded, the outcome label is wrongly recorded, it is being expanded unnecessarily, right? That will make the decision tree complex. When the decision tree is made complex, what will happen? It will not be able to generalize well with unseen data. It is okay with this combination or this combination or this combination or this combination. In that case, what will happen? When some new data point is given, it will try to predict it as no only. Actually, when the label should have been S, right? Because your new decision tree, complex decision tree H, is answering this training example, is consistent with this training example. You understood clearly? Now the addition of this incorrect example will now cause ID3 to construct a more complex tree. The result is that ID3 will output a decision tree H now, complex decision tree, that is more complex than the original tree H dash, which is having 2 levels. H is having some 3 to 4 levels now because of this new examples. But H dash, your old decision tree, is simple and it is fitting the training examples properly. And now it is not fitting because of this outlier. Understood? Think about it for a moment. Your new decision tree is made more complex now and it will fit with all the training examples. But H dash, though it doesn't fit with the new training example, it will generalize well to the unseen data. Why? Because it is more strict in considering the attribute combinations. Right? Now, there are several approaches to avoiding overfitting in decision tree learning. These can be grouped into 2 classes. There are several approaches. You can avoid decision tree in many ways. You will come across all those ways while you start working with fitting the data sets with the models, right? But let us have some preliminary idea about it, some fundamental idea about it. So that you can start off if at all you are working with some data sets, right? What are those 2 approaches? Approaches that stop growing the tree earlier before it reaches the point where it perfectly classifies the training data. Where to stop expanding the decision tree. Which point to stop expanding the decision tree. In this case, in this graph case, maybe this is the optimal point where the expansion of decision tree has to be stopped. Around 20 to 25 nodes, if the expansion of the decision tree has stopped, then the training set as well as the test set accuracy will be synchronizing, right? They'll be hand in hand, which doesn't indicate any overfitting of the data. That kind of model will generalize well with unseen data also, right? So you need to identify which is that optimal point where to stop fitting the model to the data. And the second approach is approaches that allow the tree to overfit the data. First, the tree is expanded as far as possible. The tree is constructed as complex as possible. Now, start pruning the tree. Prune means cut the nodes in the tree wherever it is not giving considerable performance, wherever it is not giving significant performance, wherever it is not showing improvement in the performance. Start removing the nodes. Okay, remove the node and see the performance with the test data. If it is not giving good performance, then you have to retain the node. If it is giving good performance, yes, the decision of pruning that node from the tree is correct. Then you have to keep that node removed from the tree. This is how you need to perform post pruning. Now, what criterion is to be used to determine the correct final tree size? What should be the criterion? What should be the factors that you need to consider in order to determine the correct final tree size? Use a separate set of examples distinct from the training examples, which is called as test example set, in order to evaluate the utility of post pruning nodes from the tree. Okay, in order to test something, you have to hide the data from the model, right? So that you give this unseen data to the model, it has to predict well with that model. Then only we say your model is performing well. If it is predicting wrong, if it is making wrong prediction with the unseen data, then we say that model is not performing well, right? This is for that you need to divide your data set into two parts. One part, that is the training set on which the model has to be trained, and the test set on which the model has to be tested or validated. Sometimes we call it as validation set also. Do not get confused. Lots of different terminologies will be used in this machine learning area, in this machine learning domain. So you need to be aware of all these terms. Training example set is called as it is, but test example set is sometimes called as validation set, is sometimes called as held out set, is sometimes called as just test set. Okay, so I'll tell you in which context how that particular name is used, right? Now use all the available data for training, right? But apply a statistical test to estimate whether expanding a particular node is likely to produce an improvement beyond the training set. If there is an improvement, yes, in that case, you can make a decision of whether retaining the node or removing the node. Now use an explicit measure of complexity for encoding the training examples. This is another method. We are not going to deal with this method, but I'm just introducing you. There is such method. Training examples and the decision tree, halting the growth of tree when this encoding size is minimized. Whenever that encoding size is minimized, then you can stop expanding the tree. That is another method. But normally most of machine learning experts follow this first part, first approach. Now, let us see two types of pruning methods. One is reduced error pruning method, and the next one is rule post pruning method. Okay, these are very simple to understand. Only thing is you need to follow the terminologies what I use, because they will be frequently used in this domain. Whenever you read some blog or an article written by some machine learning expert, actually you will find it very interesting, but you should not be alienized with the words they use. You should not feel new to the words they use. That's why focus in the class, concentrate, you will easily understand. Okay, now what is this reduced error pruning method? Let's see. How exactly might we use a validation set to prevent overfitting? See, before we called it as test set. Now we are calling it as validation set. Both are the same. Do not get confused. Now, how exactly might we use a validation set to prevent the overfitting? Let's see. One approach called reduced error pruning. The entire meaning of the approach lies in the name itself. Did you notice? Reduced error pruning means when there is reduced error, prune the node. When the error is not reduced, keep the node. That's all. That simple it is. One approach called reduced error pruning is to consider each of the decision nodes in the tree to be candidates for pruning. Consider each of the decision trees to be the each nodes of the decision trees to be the candidates for pruning. Means consider a node. If removing that node from the tree, if it is giving good performance, remove it. If it is not increasing the performance, keep it. Simple decision has to be made. Now, pruning a decision node consists of removing the subtree rooted at that node. Say if you have a decision tree like this node, if you prune, it will remove the entire subtree, right? That is what we mean here. Pruning a decision node consists of removing the subtree rooted at that node, making it a leaf node, and assigning it the most common classification of the training examples affiliated with that node, right? So whenever you want to prune this node, you're actually removing the condition on which further the tree is built. Now, when you remove that condition that will become a leaf node with classification as either yes or no. And what all training examples have the outcome label as S under this condition will be placed at this leaf node, right? And assigning it the most common classification of the training examples affiliated with that node. Do you remember in the previous previous session we have seen some D1, D2, D3 examples are here. After classification, D1, D2 come this side and D3, D4 comes this side. After classification, suppose, right? You're assigning here when this condition is satisfied, if S, how many of the training examples are following that condition and getting the outcome label as S? That has to be placed at this leaf node. How many of them are having no? That has to be placed at this leaf node, right? That is what is mentioned in the second point. Now read it, it will be more understandable. Pruning a decision node consists of removing the subtree rooted at that node, making it a leaf node. Yes, it is no longer a condition. It's no longer a split point. It is now a leaf node because that node is pruned. Right now it has become a leaf node, giving the final outcome label either yes or no, defaulter or not, reliable or not, loyal or not, like that. Okay, the leaf node will contain the outcome label and assigning it the most common classification of the training examples affiliated with that node. So what training examples will be sorted to this branch, what training examples will be sorted to this branch, keep them. That is how you need to sort them further after pruning. After pruning, some readjustments will happen in the decision tree, right? That is what is being mentioned here in the second point. Now, nodes are removed only if the resulting pruned tree performs no worse than the original over the validation set. Important point to remember. Nodes are removed only when the resulting pruned tree, means after removing that node and checking that decision tree with the unseen data, if it is giving more performance than before, then removing that node is a good decision. Keep that node removed from the decision tree. But if that decision tree after pruning is not giving good performance on the test set, in that case, you have to keep the node. You should not prune off that node from the decision tree. Try with another node. Try with another node. Keep on doing this until all the nodes' validity is checked. What will happen by the end? Nodes giving not good performance, nodes giving no better performance will be removed. Nodes giving better performance will be retained. That is how you prune the tree. So you will get a tree, final decision tree with nodes which contribute for good performance of the model. That is how you finish off the pruning of the tree. It is reducing the error. Pruning task is reducing the error. That is why it is called as reduced error pruning. Now nodes are pruned iteratively, always choosing the node whose removal most increases the decision tree accuracy over the validation set. This point is actually complementary to the other point. Okay. Other way, it is said the other way. See the third point, nodes are removed only if the resulting pruned tree performs no worse than the original over the validation set. Okay. Nodes are pruned iteratively like this, always choosing at each iteration what the node whose removal most increases the decision tree accuracy over the validation set. It's quite simple now to understand, right? I think it will be easy for you to answer this question now if asked in the exam. It's actually simple common sense. What we do outside with pruning a tree, same thing we are doing it here. By pruning a tree in the garden, it will increase the growth of the tree. Here, pruning the decision tree will increase the performance of the tree, performance of the model that is using the decision tree. That's it, right? Now let us understand it in depth. The additional line in this figure, in this graph, shows accuracy over the test examples as the tree is pruned. Did you notice this? There is another dotted line. As you keep on pruning the trees, say the decision tree initially has 100 nodes. Now you keep on pruning the tree and check the accuracy. It is actually increasing. Did you notice this? It is actually increasing. When compared to the previous dotted line, this dotted line is above this line. Did you notice that? Means by pruning certain nodes which doesn't contribute to the performance of the model's performance will obviously increase, and it will also increase its generalization capacity on the unseen data. It will try to this model will try to predict properly with the unseen data as you make it learn optimally, not more or not less. If a machine learning model learns less, it is called as underfitting. If it learns too much, it is called as overfitting. But if it learns optimally, that is what you have to decide as a machine learning expert, where to stop fitting your model with the data, with the training examples. That decision, if you are able to take optimally, your model will be the best performing model, right? The additional line in this figure shows accuracy over the test examples as the tree is pruned, as the tree is cut short, as the nodes are being removed. Okay, when pruning begins, the tree is at its maximum size and lowest accuracy over the test set, that is here. Now, as pruning proceeds, as you are cutting the nodes from your decision tree, the number of nodes is reduced, obviously, and accuracy over the test set increases. That is what we are seeing here. Here, the available data has been split into 3 subsets. The training set, the validation examples used for pruning the tree, and a set of examples used to provide an unbiased estimate of accuracy over future unseen examples. Such a long explanation, right? And it is again confusing. I said first, data set will be divided into training set, test set. Now here we are saying the the data set will be divided into training set, validation set, and test set. What is this? Why I am changing my word, you are thinking? It happens when you go on trying to increase the model performance. Sometimes, listen carefully, a data set is divided into training set and test set, where the model training takes place on the training set and validated on the test set. Right. Now, you are performing model training while pruning. Okay, you're performing an additional task of pruning and asking your model to train on the task and perform better on the unseen set. In that case, what you have to do is your data set is given, it is divided into training set, and it is divided into validation set and also the test set. Here you are making 3 parts. Now, when the model is being trained on this training set and making it perfect while validating in order to prune the nodes, means you're performing internal testing while training the model. You're not doing the validation separately here. What you're doing is, in this first case, you see the data set is divided into 70% training data and 30% test data. Now, in the second approach, what you're doing, from this 70%, again, you take part of it as training data and small part of it as validation data. Don't touch the test set, 30%. Okay. Now, from this 70%, treating it as full data set, divide part of it for training and part of it for validation. Why this validation is required for you? In order to test whether the pruning will increase the performance. Now, train the model, remove a node from the decision tree, validate whether that removing the node is increasing the accuracy or not. On the validation set, yes, it is increasing the accuracy. Keep that node removed. Now check on another node, remove that node and see its performance with the validation set. If it is increasing the performance, remove the node or keep the node. Now your model learns very well from this training and validation. Done. Now that model is tested on the unseen test set to get unbiased result. To test it unbiased. Unbiased means this test set is not seen by the model at all, not even during validation. Your model learnt well from the training set and validated for after pruning with the validation set. Now you're testing it on an unseen test set. Right? In that cases, you have the third part. Do not get confused. It depends on the machine learning expert again, whether to use 3 parts or 2 parts. Okay, always this second approach is better. Why? Because you're internally validating while training itself. Later you test it on unseen data. Okay, so this is moderate expertise that is shown by the machine learning expert, and this is best one actually. You keep on cross-validating your model while building itself. Then you test it on a separate held out set or test set, which is unseen by the model. Got it? Now you see, you'll understand this sentence. Here, the available data has been split into 3 subsets. The training examples, the validation examples used for pruning the tree. Got it? While validating it itself, you will try to prune the nodes. Now, another set of test examples is used to provide an unbiased estimate. Why we call it as unbiased? It didn't see the training test examples at all. In that case, it doesn't have any partiality in prediction. It predicts correctly, unpartially. That is why we say the test set is used to provide an unbiased estimate of accuracy over future unseen examples. You know that test set is hidden from the model. That is why it is unseen by the model. So we can validate it properly when the test examples are tested with the model. I'm repeating again, training examples and training example set and validation set is actually one training set. So that when the model pruning happens, it validates its decision with this validation set and it learns. Now the model is ready, test it with the test set. Okay. Now the plot shown here shows only accuracy over the training and test set. Accuracy over the validation set for pruning is not shown in this graph. Do not get confused, okay? Only the training set and the last third part, test set, is shown here. Okay. Now, it depends on the decision of machine learning expert to divide the data set into 2 parts or 3 parts. And also, the size of the data set matters here a lot. If the data is very small, can you make it into 3 good enough sized parts? It is not possible, right? If you have only 10 data points, in that 7 you use for, 6 you use for training, 2 for validation, 2 for testing, your model may not be trained sufficiently. That is why amount of training examples in the data set also matters. If you have 1000 data points in the data set, you can make it into 3 parts, but you have only 50 data points in the data set, then you may have to go only for 2 parts, not dividing it into 3 parts. Okay, so it depends again on the context. It comes with experience, how to decide how many parts you have to make in order to train the machine learning model. Now, if data is limited, what has to be done? They are showing us. We'll go for another method called as rule post pruning. Say you're not able to divide your data set into training set, validation set, and test set because your data set size is very small. In that case, they again provided us with a different kind of avoiding overfitting of the data. What is that approach? Rule post pruning. In practice, one quite successful method for finding high accuracy hypothesis is a technique we call as rule post pruning. Rule post pruning involves the following steps. What are those steps? Infer the decision tree from the training set, construct the decision tree from the training set, growing the tree until the training set is fit as well as possible, and let it overfit, allowing overfitting to occur. Let it overfit, not a problem in the initial stage. Construct the entire decision tree consistent with each and every training example in the data set. The tree is completely built and it is also overfitting. It is covering all the possible examples in the data set. Now, convert the learned tree into an equal set of rules by creating one rule for each path from the root node to a leaf node. I'll show you how to create the rules. If overlook equal to sunny, if humidity equal to high, then outcome label is S. That is one rule. Outlook is rainy. In that case, outcome label is S. That is one rule. Like that, you construct the rules for each and every possible path. Now, prune or generalize each rule. How do you do that? By removing any preconditions that result in improving its estimated accuracy. Remove and see a precondition. If it is improving the accuracy of the model, remove it. If it is reducing the accuracy of the model, keep the rule. It may be important. Okay. Now sort the prune rules by their estimated accuracy. Okay. And consider them in this sequence when classifying the subsequent instances. Sort the prune rules by their estimated accuracy. This rule when pruned is giving this accuracy. This rule when pruned is giving this accuracy. Sort. Now the topmost rule will be giving the most accuracy if you are pruning it. Keep it pruned. Keep it removed from the decision tree. Okay, that is what we mean by the fourth point. Now in rule post pruning, one rule is generated for each leaf node in the tree. For this, one rule is generated. Can you tell me what is the rule? Outlook equal to sunny and humidity is high. Then what is the post condition? Means outcome label? No. Generate another rule, outlook equal to sunny and humidity normal. What is the post condition? What is the leaf node? Yes. What is the outcome label? Yes. Right? That is how you need to generate the rules. Now, can you tell me the rules for this part, students, quickly? Does it take so much time to unmute and answer, students? Can you tell me the rule on right side of the branch of this tree? Can I get an answer from you? What is the rule you can make? General English, right? You can answer very easily. When outlook equal to rain and wind equal to strong, that is the precondition. What is the post condition? What is the outcome label? No. When you take this branch, when outlook equal to rain and wind is weak, what is the post condition? Yes. This is how the rules have to be constructed. Now, removing a rule will increase the performance of the tree means remove that. If it is not increasing the performance of the tree, retain it, keep it. Okay. Each attribute test along the path from root to the leaf becomes a rule antecedent. Means outlook equal to sunny, and humidity equal to high, that is called as precondition or antecedent before, left hand side. And the classification at the leaf node, that is this leaf node no, becomes the rule consequent, right hand side, that is post condition, right? You can see the example here. If outlook equal to sunny, this part we are seeing, and humidity is high, that is the precondition, or it is also called as antecedent. And then what is the outcome? Playing tennis equal to no. That is called as post condition, or we can also call it as consequent. Result of a precondition, the consequence of a precondition is called as consequent, right? Or a post condition. Now, each such rule is pruned by removing any antecedent, that is the precondition, whose removal does not worsen its estimated accuracy. If the estimated accuracy is being reduced, worsened, becoming worst, in that case, don't remove that rule. That is important rule. But if it is increasing the accuracy after removing that rule, it is a good decision to remove that rule. Okay, that is called as post pruning. Why we are calling it as post pruning? You are allowing the tree to be built completely and building the rules on that decision tree and removing the rules which doesn't contribute good to the performance of the decision tree or to the performance of the machine learning model. That is why you call it as rule post pruning. Now, no pruning step is performed if it reduces the estimated rule accuracy. Correct, right? If the accuracy is reducing further, then don't perform any pruning. That rule is very important for the decision tree. That branch is very important for the decision tree. Keep it. Okay, this strategy is followed by rule post pruning. Now, why convert the decision trees to rules before pruning? There are three advantages. There are some advantages, not three, many are there. There are some advantages. Let us see what are those advantages. Converting to rules allows distinguishing among the different contexts in which a decision node is used. Right? If this is true and this is true, we are able to understand the situation very clearly if the rules are built. And in contrast, if the tree itself were pruned, the only two choices would be to remove the decision node completely or to retain in its original form. Right? If rules are there, the decision of removing that rule or keeping it will be more clear for us than removing directly the node itself, like we do in reduced error pruning. Okay, so this is more explainable to the machine while we are performing this pruning task. It is more interpretable by the machine learning expert when the pruning is being done. He can understand it better. Now, converting to rules removes the distinction between attribute tests that occur near the root of the tree and those that occur at the leaf nodes. It is easy to distinguish between the attribute tests we make if rules are there. Thus, we avoid messy bookkeeping issues such as how to reorganize the tree if the root node is pruned while retaining part of the subtrees below this test. Right? If you are pruning a node, that entire subtree have to be removed. While removing it, you have to keep a bookkeeping of the classification that is done onto the leaf nodes. These many training examples fall in this leaf node. These many training examples come under this leaf node. When that subtree root is removed, then this all data have to be put as leaf nodes to the main branch. Okay, lot of tracking have to take place. But with rule post pruning, it doesn't happen. It is very easy to check. And converting the rules improves readability. As I said, interpretability will be increased. Readability, understandability can be increased. Rules are often easier to understand when compared to directly working with the nodes and removing them. That is why in practical usage, rule post pruning is more used than reduced error pruning. Now in next lecture, the other 4 issues under this decision tree learning can be discussed. Any doubts still here, students? Is the concept very clear? Okay, then we'll meet in the next class and finish off the discussion about issues in decision tree learning.